So why the groundwater is important? If you see the water balance of the earth, you can see 97.5 percentage of water is present in the ocean, whereas only 2.5 percentage of fresh water is available at global scale. Even in that 2.5 percentage, 68.9, almost 70 percentage is in the form of glaciers or permanent snow cover, which is not readily usable by us. 0.9 percentage is included in the soil moisture, swamp water, or permafrost, which is also not usable by us. And 0.3 percentage is present in the fresh water, is present in the lakes and river storage. Only this portion is renewable for us. So in such a case, 29.9 percentage is fresh water available in the form of groundwater. Even the surface water is also mostly contaminated, which is not readily usable for us. So we mainly depend on this 29.9 percentage of fresh water, which is available within the ground. That is why the groundwater is considered to be very precious one. Where this groundwater is stored. This groundwater is stored in the aquifer. So then what is aquifer? Aquifer is derived from the Latin term meaning water bearer. That means it is one kind of geological formation. So geological formation means it can be rock, it can be clay, it can be sand, anything. All these are geological formation only. But aquifer is the one type of geological formation which is capable of storing water, and when we put a well into it, even it can yield more amount of water. So groundwater occurs in any geological formation. Aquifer is one of the important geological formation. An aquifer may be defined as a geological formation that contains sufficient permeable material or lithological unit or collection of unit which are capable of storing and yielding, as I said before. These are some of the example. These are some geological formation which is called as aquifer. So sandstone, it has too many pores where the water can be stored within the sandstone. Then alluvium. Mostly alluvium means this kind of geological formation is present near the water bodies where more amount of water is absorbed and stored by the geological formation. Then basalt is also one kind of aquifer. These are examples of aquifer. Now you know very clearly aquifer is a geological formation which is capable of storing water and also yielding water when we put well into it. There are different types of aquifer. One is unconfined aquifer and other one is confined aquifer. So unconfined aquifer. This type of water bearing formation underlined by impermeable layer. This unconfined aquifer is also called as water table aquifer. So the upper surface of the aquifer is the water table, and water table aquifers are directly overlain by an unsaturated zone or a surface water body. So you can see in this figure very clearly it will define the unconfined aquifer. This is our land. Now when it is raining, this unconfined aquifer can have unsaturated zone, intermediate zone, and then it will have a saturated zone below which we have a impervious layer. So this entire portion, if we just see here, this entire portion is called as unconfined aquifer. So, in unconfined aquifer, water table is the upper boundary. This area is the upper boundary and impermeable layer is the lower boundary. So this zone from here to here, it is called as unconfined aquifer. This aquifer is underlined by a impervious layer. The impermeable layer underlying and unconfined aquifer is also known as free aquifer or phreatic aquifer or water table aquifer and non-artesian aquifer. Depending upon the inflow and outflow, water table will fluctuate. What is the meaning? In case it is raining, in such a case, water table will rise. So the aquifer thickness may be increasing. Okay, then now we are continuously pumping out the water. That time the water table will be lowered. So the water table will be fluctuating season wise or daily. Depends upon the what kind of input or output taking place in that particular aquifer. A well driven into an unconfined aquifer will indicate a static water level corresponding to water table level at that location. Now I want to know water level in this area. So I need to drill a well. Then I can get to know where the water is present. That is what given in this sentence. So this unconfined aquifer, the pressure in this water is atmospheric pressure. Okay. And the water in this unconfined aquifer easily susceptible to contamination. Just like the directly surface contamination may influence the unconfined aquifer if the wells are not properly lined. Now, the next type of aquifer is confined aquifer. So, from the term, English term, confined means in between two things. Okay, here also, this is the aquifer, confined aquifer. Above that unconfined aquifer, this is impervious layer, and below that also we have a impervious layer. So this aquifer is confined between two impervious layer. This is called confined aquifer. So this portion can be considered as an unconfined aquifer, and this is impervious layer, then again aquifer, then again impervious layer. Okay. Now we will see whenever see an aquifer that is immediately overlined and underlined by a low permeable unit is called as confined aquifer. A confined aquifer does not have a water table. So the water level in the confined aquifer will rise above the confining upper layer. You see here, we have drilled well. It is piercing through the impervious layer and going to the aquifer. When the well is drilled, the water level is going above the impervious upper layer. See here, confining upper layer. This level is termed as piezometric head or pressure head. Now, if the piezometric head in such aquifer is above the ground surface, it is known as artesian aquifer. You see here, the well is drilled in the confined aquifer. Now the water table is going above the ground level. It is not within the ground like here. It is gone above the ground level. In such a case, the aquifer is called as artesian aquifer. So, water level in the piezometer is a measure of water pressure in the aquifer because water held in this confined aquifer is always under pressure. The recharge of confined aquifer normally takes place where they are exposed to ground surface. You see here it is impervious layer. This zone, even if it is raining, water will not penetrate into this confining aquifer. Maybe it will get into this unconfined top layer. Then how this confined aquifer is getting water? This confined aquifer is somewhere open into the atmosphere. When it is raining, that water is getting recharged in this place. If you see here, this aquifer in this area, it is considered to be an unconfined aquifer. Whereas wherever it is getting pressed from the bottom as well as in the top, it is becoming a confined aquifer. So the recharge of confined aquifer normally takes place where they are exposed to ground surface. Water pressure in the confined aquifer is higher than the atmospheric pressure. Example, sandy layer between two granite layer, sandstone layer between two layers of shale. These are examples of confined aquifer. Then other geological units, but they are not aquifers. Okay, so aquifer is a geology which can store water, but we have other geological unit. If we just see here, the impervious layer, that is also one kind of geological unit. A clay is one kind of geological unit. Okay, now you have one term, aquitard. As saturated, it can get saturated, but poorly permeable formation which delays groundwater movement and does not yield water freely to the well. You see here sandy clay. Clay will store water. It will take time for it to store. But even if you drill a well, you cannot pump out the water. Even sometimes leaky aquifer. Then aquifuge, impermeable formation cannot store, at least clay can store some amount of water. But when you talk about aquifuge as a geological formation, it cannot store or transmit water. It has no conducting capacity, it has no pores. So that is what this impervious layer. They are called as aquifuge. Then aquiclude. So saturated, it is also saturated, but relatively impermeable material that does not yield appreciable water to well. These two, aquitard and aquiclude, what is the difference? Here it is completely clay. Here it is a kind of sandy clay. That is, clay is dominating, but still sand will also be present in the aquifer. Okay, these are the other kind of geological formation, but they cannot yield good amount of water to well. Now, let us study aquifer parameters. Our interest is on this aquifer only rather than aquitard, aquifuge or aquiclude. Okay, so it has certain parameter that describes how much water this aquifer can give out whenever we are drilling a well, or whenever it is raining, how much water this aquifer is capable of storing it, how much water it can recharge. So these properties only deciding the capabilities of that aquifer. What are those parameters? Porosity, specific yield, specific retention, storativity, transmissivity, hydraulic conductivity, hydraulic gradient, aquifer thickness, static water level, all these are considered to be aquifer parameters. Now let us concentrate on this porosity, specific yield, specific retention and storativity. Now let us see what is porosity. Porosity is nothing but the pores. You see here, you have these are some small sand where the water will be stored whenever it is raining. Whenever it is raining, water will be stored in this pore spaces only. Okay, so the porosity is nothing but ratio of volume of pore space to the volume of formation V is called the porosity, usually denoted by N. So, in a simple way, you can consider this is the total volume. So, this is total volume. VV is nothing but only the pores present in it. Volume of voids divided by total volume into 100%. That is porosity. In reality, in the lab, how we can estimate the porosity? You can take one measuring cylinder, you can fill it with the sand. Okay. Now you can simply pour water until it is getting saturated. You measure the volume of water which you have used to fill that pores. So that volume is the volume of voids. The remaining, you know, the volume of cylinder, diameter and the height, you will get the total volume. This is a simple method. It is not very accurate, but this is one of the simple method which is used to understand the porosity. Okay. So now, if you see igneous or metamorphic rocks, it is low primary porosity, can have high secondary porosity. So what is the primary and secondary porosity? During the formation of the geological formation, pores will be there. That is primary porosity. Secondary porosity, after that it may undergo weathering, because of that cracks will be there. That is called as a secondary porosity. The secondary porosity will be very larger than the primary in the size. So porosity ranges for sediment. Well sorted gravel. If you have a gravel, it will have very high porosity, 25 to 50 percentage. Sand and gravel mix, 25 to 35. Glacial till, 10 to 20 percentage. Silt, 35 to 50. Whereas clay, 33 to 60 percentage. Now, let us see specific yield. What is specific yield? Now, here we have seen it was we had only the sand in the ground. Now it was raining and completely it filled the voids. You assume like that. Now the voids are completely filled with the water. Specific yield is nothing but now we are putting one well in that aquifer, small formation. Okay. How much water can be pumped out from this area, from this volume? How much water we can pump out? That is called as specific yield. Okay. Volume of water that can be drained by gravity or pumped against gravity from a given volume of an aquifer is called specific yield. Okay. Because you assume 100-meter cube of water got into the aquifer in this cube. Okay, 100-meter cube water gone into it. Now I am putting a well. We cannot always take out 100-meter cube of water out from the aquifer. Only some amount of water can be pumped out. Maybe 90-meter cube or 80-meter cube. It depends upon the type of geological formation. Remaining 10 to 20 percentage, it is approximate I am telling, that will be held within the aquifer because of the surface tension. So specific yield, and it is just by the gravity. Even if you don't pull out by the pumping, just if you drain the aquifer, if you pour and automatically that water will be coming out. That is the amount of water. So volume of water that can be drained by gravity or pumped against gravity. So this is the specific yield. In common, you could have told the well yield is this much. So that is the term here. We have formula for specific yield. Specific yield is nothing but volume of water pumped out divided by volume of sediments drained, total volume. Okay. So specific yield is having certain value, that is 0.02 to 0.3. This is how why it is varying depending upon the type of aquifer material. The specific yield will vary. The value of specific yield depends upon the grain size, shape and distribution of pores. Now, these are the various specific yield values. What are the material? Coarse gravel, medium gravel, fine gravel. Likewise, it is given. In an average, the specific yield will vary from 2 to 22. This is aquifer material. It is always heterogeneous. Okay. So you see here 2 to 22 is the range of specific yield. Now, specific retention. As I indicated before, whenever we are pumping out, it is not always possible to completely drain out the aquifer. Some amount of water will be held in between the pores due to the surface tension. The amount of water which is held against the gravity is called as specific retention. So, all water cannot be drained by gravity or by pumping from wells. Some portion of water is held in the void space by molecular and surface tension forces. This phenomena is called specific retention of aquifer. So now, can we write like this? Porosity, which is nothing but total volume of voids, which is equal to specific yield plus specific retention, because the porosity is nothing but volume of voids. So now completely water is filled in that volume. Now some amount of water is pumped out, that is specific yield. Some amount of water is held in that space itself, that is specific retention. So porosity is equal to specific yield plus specific retention. These are the specific yield value. Clay is 2%, silt 18%, sand 26%. So this is a simple figure, same concept to understand. You have a aquifer without any water. Now it is raining. The voids are filling the rainwater is filling the voids, that is pores. Now it is completely filled. Okay. Now we are pumping out the water. Some of the water is coming out, some water is held in between the pores. The water which is coming out is specific retention. The water which is held in the aquifer is coming out is specific yield. Water which is in the aquifer is specific retention, which is nothing but the total porosity. Now, let us do this problem. Now, in an area of 100-meter square, you assume it like this. 100-meter square, water table is dropped by 4.5 meter. You assume this is initial water level, 0 meter. Okay. Now it is dropped by, this entire thing is aquifer only. Maybe we are pumping. Okay. The water level is dropped by 4.5 meter. If the porosity is nothing but 30% and specific retention is 10%. They are asking us to determine the specific yield. We know the relationship porosity is equal to specific retention plus specific yield. So 30% is equal to 10% plus specific yield. So now specific yield is equal to 20%. Now we got to know what is specific yield. The second part of this problem is change in groundwater storage. After they pump out, how much volume? Okay, so maybe this you had full of water here. Here now, this much is pumped out. That means how much volume we pumped out, or how much volume, what is the change in the volume. This is what we are trying to understand. For that also we have formula. Specific yield is equal to volume of water pumped out divided by volume of aquifer. So here specific yield is 20 percentage. We don't know how much is the volume of water pumped out. Volume of aquifer means the area into height. That means how much it is pumped out. Water table drop. They have dropped for 4.5 meter. So 20 percentage X area is nothing but 100 meter square. For how much volume it is pumped out? For the height 4.5 meter. Now volume of water pumped out is equal to, that is change in groundwater storage. Volume of pumped out is equal to 0.2 into 100 into 4.5. That is the volume of water pumped out from this aquifer. So if you just check this into 100 into 4.5, it is 90 meter cube. 90 meter cube of water is pumped out from this aquifer. So this problem is over now. If it is a tub, see, generally what we think, you have some bucket, okay? You have some rectangular kind of bucket or tin. Now simply if they say 4.5 and this is 100 meters squared, you will tell volume pumped out is area into height, 100 into 4.5. But it is held in between the sand pores. Just like that, we cannot write this as a volume of water pumped out from the aquifer. Okay. So, what kind of porosity present in that? That is indirectly considered in the specific yield value 20 percentage. So, 20 percentage means what kind of aquifer approximately it is? 20 percentage means it comes around silt to fine sand. That is a kind of geological formation which was present there. So generally specific yield is a term associated with the unconfined aquifer. Now we are going to see another term, that is storage coefficient or storativity. That is what water that a permeable unit will absorb or expel from storage per unit surface area per unit change in head. This is also very similar to unconfined aquifer. How much volume is pumped out from a confined aquifer, we termed as storage coefficient or storativity. The storativity value ranges from 0.00005 to 0.005, indicating that large pressure changes over extensive areas are required to provide substantial water yield. Same formula. So if you want to pump out water from the confined aquifer, you need more area because of this storativity value. In case of confined aquifer, it is decline in piezometric level. In case of unconfined aquifer, decline in water table. This is how we call. Confined aquifer means whenever we pump out, we tell decline in piezometric head. Okay. In case of unconfined aquifer, we call it as a water table. Definition wise, both are considered to be same. Volume of water pumped out per unit surface area per unit change in head. Now, we will see some example. It can be useful for civil engineers or geologists. What are the scenario we can have? Sometimes in one area, it is raining. Okay. After the rain, for the given volume of rainfall, okay, area into of rainfall, some amount of water is getting in. Because of that, how much water level is getting improved in that water, in that area? We are going to identify, especially using this specific yield and storativity. We have some of the scenario. Let us do some problem. This is one example. Now let us see this example. Assume that there are two aquifers. One is in artesian condition. What is the meaning? Artesian condition aquifer means confined aquifer. When we drill a well, the water due to pressure, it is coming out of the ground level from the confined aquifer, from the well drilled in the confined aquifer is called as artesian condition. Okay. The storativity is corresponding to confined aquifer, whereas specific yield corresponds to unconfined aquifer. And other is unconfined aquifer, that is specific yield. Sy is nothing but specific yield. Okay. So first, calculate the volume of water pumped out for construction purposes from a 1 kilometer area of both confined and unconfined aquifers, given that pumping has resulted in a decline of hydraulic gradient. That is, the water level is declined by 2.3 meter. What they are asking, for construction purpose, they have pumped out some amount of water. Because of that, the head change is 2.3. Do not worry about what was the initial head. Let always you assume initial head as 0 as a level. And then after pumping, it has gone down to 2.3 meter decline had taken place. Okay. The difference you understand. That's all. Now, area of the aquifer is 1 kilometer square. So, first time we will assume it as a confined aquifer. Next time we will confine as a unconfined aquifer. Let us see how much volume of water we are able to pump out. So let us solve this problem. So case 1, we will consider it as a confined aquifer. Confined aquifer means storativity. Same formula. Okay. storativity is equal to what they are asking, volume of water pumped out. We will write the formula. Pumped out divided by area into height of pumping or decline in water level or change in water level, anything you can consider. In this problem, the storativity, given storativity, you see here for confined aquifer 0.0045. 0.00045. This is unknown. Now, area is 1 kilometer square and the change in hydraulic head is 2.3 meter. 1 kilometer square, kilometer is 10 power 3. And just consider it as 10 power 6 square. Then decline 2.3 meter. So now volume of water pumped out from confined aquifer is 0.0045 into 1 into 10 power 6 into 2.3. This is meter cube. So let us see how much it is coming. If we calculate 0.045 into 1 into 10 power 6 into 2.3. This is coming around 1035 meter cube. Now even they are asking if it is an unconfined aquifer condition, how much water the engineers have pumped out. Okay, so now here this is specific yield. So specific yield. Specific yield is nothing but volume of, same formula you can write, volume of water pumped out divided by area into height of pumping. Maybe this class will be over by in few minutes. So now the specific yield. What specific yield is given in this problem? The specific yield is 0.2. Okay. So same area only. 1 into 10 power 6 meter square into 2.3. Same decline also. In this case, how much is the volume pumped out? So now if we just multiply everything, 0.2 into 10 power 6 into 2.3, which is equal to 4,60,000 meter cube. Can you note down the huge difference? Same area, same water level decline, but still from the confined aquifer, we could pump out only 1035 meter cube, whereas in unconfined aquifer, 4,60,000 meter cube of water we are able to pump out. This clearly shows unconfined aquifer, draining of aquifer is taking place. Whereas in confined aquifer, the pressure is getting released from the confined aquifer. We need more amount of area in order to get less water. So for the same area, okay. In this case, the well is drilled in the confined aquifer, whereas in another case, well is drilled in the unconfined aquifer. That is the main difference. Now, let's do the second part of this problem. Now, due to rainfall, 100 cubic meter of water. Due to rainfall, 100 cubic meter of water. Maybe you assume this is your aquifer. Now it is raining. 100 meter cube is raining and water is added instantaneously to both aquifer. So maybe your house is here and your college is here. Everywhere it is raining. Here also 100 meter cube. In your house also 100 meter cube. Maybe, but your house is located in unconfined and college is located in confined. Okay. How much will be the groundwater head lies? So in both the area, what is the groundwater level rise because of this 100 meter cube? This is what they wanted to know. Okay. So now let me assume same formula. Unconfined aquifer. Unconfined aquifer means specific yield, volume of water divided by area into change in height of water. Whether you pump out, you add everything here because of adding or pumping out, what is the change in height of water? So, unconfined aquifer, it is 0.2. Volume of water added to the aquifer. Now it is raining, rain is falling. So, this volume of water can be amount of water pumped out or amount of water getting into the aquifer. This volume, it can be addition or pumping out. Now in this case, the rainfall is coming. It is addition. 100 meter cube. Same area. 1 kilometer square. 10 power 6 meter square. We don't know how much is the change in height. H is unknown here. So again now what is height? That is what we need to find out. In near your house, this is your house, we consider it as an unconfined aquifer. Because of the rainfall, how much water level improved in your house, near your house? So, X same 100 meter cube divided by 10 power 6 meter square into 0.2. Now, if you see 100 divided by 10 power 6 into 0.2. So, change in 0.005 meter is the rise in water level. Okay. Now, let us see how much water level took place in confined aquifer near college. Okay. Near your college. So, now confined means storativity. Same formula. Volume of water added or pumped out, anything it can be, divided by area into change in height due to the pumping or recharge. So here S is 0.005 004. Volume added is 100 meter cube divided by area 1 kilometer square, that is meter square, into change in head. Now, if we just see here, 100 divided by 0.004 into 10 power 6. It is 0.25 meter. So, even for this small change, this much water can be recharged. But whereas here, only when we recharge or pump out, we need to decline 0.25 meter depth. Then only this 100 meter cube of water. We can't get all the 100 meter, but just 100 meter cube of water. If you want to pump out from confined aquifer, you need to decline the water table for 0.25 meter. Whereas here, if you decline it for 0.005 itself, you will get 100 meter cube of water. Now let us see the third case. The third case is nothing but for the same given data, if 1 kilometer of water table aquifer releases certain volume of water, when the water level drops, then how many kilometer of a confined aquifer would need to be pumped to release the same volume of water? Already we found out how much water we could pump out from the unconfined aquifer. That is 4,60,000. We can pump out 4,60,000 meter cube of water from unconfined aquifer. Now, we need to, for which area? For 1 kilometer square area, and decline is 2.5. 2.3. Now they are asking how much area if we want to pump out same volume for the confined aquifer. We'll use the same formula. We'll not worry. Okay. Confined aquifer formula is storativity is equal to volume of water divided by area into height. So now volume of water, how much we could pump out from the confined aquifer? This much amount. Area only they are asking, that is unknown. Height is same 2.3. Now this storativity is 0.43. So for this, now let us see how much area is required if you wanted to pump out this much amount of water from this. Okay, so the area would be 46,000 divided by 0.043 into 2.3. 46,123 divided by 0.00043 into 2.3. Oh my God, we need 46,516,280 meters square in order to pump out this 4,60,000 meter cube of water. Okay. Thank you. With this, we are completing this.